So if anybody has questions for Roland, go ahead and chat him over the chat here in the next few minutes. And we're going to get started with the next talk, who is the next presenter is Reid Viegut. He is a master's student with the University of Missouri. And he is with the USGS Cooperative Fish and Wildlife Research Unit there. He's presenting on his master's thesis project for the next couple of years that he began in August. And it is titled, his title today is Assessing the Feasibility of Using Small Unmanned Aircraft Systems and Artificial Intelligence for Monitoring Waterfowl Abundance. Thanks for being here, Reid, and you have the floor.
All right, thank you. As Julie said, my name is Reid Viegut, and I'm part of the Missouri Cooperative Fish and Wildlife Research Unit at the University of Missouri. And this is a collaborative project with the Missouri Department of Conservation and the Computer Science Department at the University of Missouri. And it's part of my master's thesis project of assessing the feasibility of using small unmanned aerial systems and artificial intelligence for monitoring waterfowl abundance. So the first problem with aerial surveys are they're conducted from fixed wing aircraft, and they're incredibly dangerous to wildlife biologists, and they're actually the leading cause of work-related mortalities among wildlife biologists. They are also expensive and unreliable, and the results depend on the detectability of species in the environment, the experience of the observers, and movement of birds due to the disturbance of the aircraft. The other main way to count waterfowl are ground counts, and these are typically very time intensive and biased due to poor visibility. As you can see in the image on the right there, the ducks in the back would be very difficult to get an accurate count on due to densities and vegetation. So overall, repeated monitoring of these populations across large areas are very expensive, and it's very hard to adequately conduct these population surveys. So we need to monitor these waterfowl populations to inform management and conservation decisions towards the North American Waterfowl Management Plan. And these decisions provide the basis for improving habitat quantity and quality for waterfowl, establishing harvest limitations, and ensuring the sustainability of resources for the future. Unfortunately, the lack of standardized methods creates uncertainty between counts and between regions, hindering the opportunity for these managers to learn collectively from management decisions in other areas of the state or even between states. Currently, the Midwinter Waterfowl Survey across the United States and Canada is used to quantify wintering waterfowl numbers in the states and some Canadian provinces. Conservation agencies, land managers, and conservation planners use these indices generated from these yearly surveys to direct wetland conservation, management activities, and evaluate harvest regulations. So these surveys are very important, and the accuracy of these surveys are important to establish these indexes of the populations. So why UAS? So in recent years, UAS have emerged as this new technology, and they've been shown that they might be able to be used to monitor wildlife populations. They provide a safer alternative to these traditional aerial surveys and monitoring techniques. They're also more cost effective, and they provide more flexibility and usability. For example, some of our flights, we schedule 1 or even just 2 days in advance, versus with fixed wing flights, you have to schedule weeks or months in advance. They are also more accessible and easier to use. For example, I'm one of the pilots that we use to fly the UAS and collect data, and both of our pilots here are students at the university. So UAS have already been demonstrated as being effective in wildlife monitoring and some population surveys, and there's papers that have shown that these counts with the UAS have been highly correlated with ground estimates. However, there is still little research that's been done on the effect of these surveys on avifauna and other easily disturbed taxa, including waterfowl. Although that they've been demonstrated as being effective in these monitoring surveys, it takes a lot of time to review and analyze these images and manually go through and count the birds in the images. So artificial intelligence and photo detection may be a solution. It's been shown that it can be 20 times faster to review these computer-generated detections than to go through and manually identify every bird. So here's an example of large object detection by a computer. This is actually from a Facebook algorithm that was used to identify these different objects. However, detecting and counting small objects like waterfowl remains extremely challenging because small objects have lower resolution, less information, and the algorithms to identify small objects are very robust or very new and still in development. So you can see this image on the right, how small some of these waterfowl might be, especially at higher altitudes with the drone, where you can cover larger distances. So the goals of the project are to assess the feasibility of using the UAS to improve monitoring of waterfowl populations by developing survey alternatives to the traditional methods of aerial and ground surveys. This will increase the capabilities of waterfowl biologists to employ adaptive approaches to management in real time using up-to-date current information collected through a systematic process that allows for collaborative learning and constant improvement of these management actions to achieve the desired outcomes either across the state or across the region. So the first research question with the project is what factors influence waterfowl disturbance level in response to these surveys? And so we want to see the difference in waterfowl disturbance level between the three different types of surveys: ground, drone, and then the manned aircraft surveys. And we want to see how the different conditions influence these disturbance levels as well. The second question is what factors of image quality affect the ability to identify individual waterfowl and estimate the waterfowl abundance, and under what conditions can imagery of this quality be collected. So we need to see how the height and speed of the drone, how the environmental factors and the habitat influence detection as well. And so the third, the overall, what is the feasibility of estimating these wintering populations on the managed wetlands in Missouri? And so that involves designing surveys and correction factors to precisely and accurately estimate the waterfowl on these wetlands. So the study site are 3 intensively managed wetlands on conservation areas created and managed specifically for waterfowl and waterfowl hunting opportunities through the Missouri Department of Conservation. So the conservation areas are Eagle Bluffs, Grand Pass, and Fountain Grove, and they're all located along major rivers that are part of primary waterfowl migration corridors. And these areas were selected due to their extensive habitat regime and the high numbers of waterfowl that stop over or winter at them. And so the areas have refuges as well as hunting opportunities on them. So you can see the differences between areas that might be hunted versus areas that no hunting is allowed. And so these are 2 of the sites. On the left, we have Eagle Bluffs, and then on the right, it's a flock of snow geese at Grand Pass Conservation Area in Missouri. So in order to answer these questions and collect the data and collect the images, we kind of have a 7-step process that we're developing to eventually estimate the waterfowl populations. So the first, we have to define the area in which abundance is estimated on a map. So for example, we choose to select a wetland pool that we're wanting to survey. Then we input the parameters of the flight into the flight. So drone height, drone speed, camera settings, all of that we input into the app we use to control the drone. Then we generate a flight plan, and we're using a grid-shaped flight plan to fly the drone over the wetland. Then we launch the drone through the flight plan, and it flies autonomously and collects images over the wetland. We then run our deep learning models to detect and count the number of birds in each image. And then we use that to estimate the number of birds in that entire region that we want to survey. We then want to generate a heat map of bird distribution so that you can compare that to vegetation or water levels or whatever else might be helpful to these managers, so that they can improve the habitat for the waterfowl. So this is the app we currently use to fly the UAS. It was created and modified through the computer science students at Mizzou. And so you can see that we have the camera settings that we can manipulate. We can manipulate the height and the speed and the overlap. So we have the height and the speed, and then adjust the overlap. And the overlap is just how each image is selected. So you generate your area, and then you can see that it will actually generate this black line to optimize the flight path through the area to collect the images. So we've been collecting images this past fall. And so one of the things we're looking at is what kind of images we need to collect and how that might change detection through by the algorithm. So visibility bias has already been shown to be a primary source of error when estimating population sizes from aerial surveys. And we expect visibility to be lower in habitats with vegetation that would cover up waterfowl, such as standing corn or forested cover types, while more open water is expected to have higher visibility and a higher detection of the birds. Other environmental variables that might influence detection can be sun or sunlight, vegetation, ice, snow, different aspects like that. So here are two examples of images taken on a cloudy day and images taken on a sunny day. And you can see on a cloudy day, you have much more or much less shadows, especially in those standing flooded corn crops. And so that might impact the detectability of the algorithm as well. And then lastly, bird density may influence detection by the algorithm. So on the left, you can see that we have a much less dense concentration of birds than the snow geese and blue geese on the right, where it's a very high concentration of the geese. And so to develop the algorithm, we fly the drones according to the flight path and take the images. We then label the images with humans to generate what we consider to be the ground truth for the image. Then we run the learning models to detect and count the number of birds on each image. And then we compare the outputs to what we labeled as humans to see, how the algorithm. So that's how we kind of evaluate and select the different algorithm to refine. So here's an image of the birds in the flooded corn and outside the flooded corn. And the blue bounding boxes around the objects are what the computer identifies as a bird. And so we have what we call false negatives and false positives. And so a false positive is an example of this top blue box here, where it identifies a piece of corn as a bird. And then a false negative would be where it does not detect the bird as the bird. So it just ignores it. And you can see that. So there you have false positives with the corn. And then here, you have a different moist soil unit type of vegetation, but you can see that some of these birds, like this bottom bird, actually has vegetation going across the bird, and it is still able to identify it as a bird. So we're still kind of in the process of figuring out what the computer sees and what the computer thinks is a bird and doesn't think is a bird. So to evaluate the algorithm, there's 3 metrics we use: precision, recall, and F1 score. Precision is basically out of the total number of predicted positives, how many of them are actually positive. So it's the true positives plus false positives divided by the true positives. So if you don't want any false positives, you would use this metric. Recall is how many of the actual positives our model labels as positives, so it's correct positives. So it gives a high cost if you don't want any false negatives. And then F1 score is a harmonic mean of precision and recall, and so it's kind of a balance in between. So I'm evaluating the algorithm. So we started with a very simple training method where we just used the outline of the birds and told the algorithm, this is a bird, and I want you to count the birds. And then we added one where we had the birds plus the background, and then we added just more information into the algorithm. And so you can see that over time, the more complex training data we used, the better the algorithm actually got, until we were getting like 90% success. And so we also want to see how different habitats influence the algorithm as well. So we have these different example habitats that we then ran through the algorithm. And you can see that the more open habitats or less complex habitats, like the levee in the land or moist soil with open water, they perform better than the standing corn, which was the lowest performing with the algorithm. So that is just overall bird detection. But what about species? Because sometimes species is important and we want to know species. So we're currently in the process of labeling and developing data with species. So we created this interface where it will bring up, it labels the birds or selects the birds with the computer, and then it brings up an image of the bird. And so then all you have to do is click and select which species of bird it is. So it greatly increases or reduces the speed and process, or increases the speed, reduces the time it takes to label the images, so that you can label lots of birds and lots of images very quickly to develop this training data. And so then it creates, these species. So it's, these are mallards. So it will then add the name to the bird. And so then we can create these species ID libraries. So we are able to better make sure we're labeling consistently, and the birds are correct. So it has this database of all of these are mallards. So if it looks like these, it's probably a mallard. So that's kind of how you can train the algorithm for the species. And so then for preliminary observations of behavior response to the drone versus the other surveys, here we have a video on the left of what it looks like when there's a helicopter. And then the video on the right will be during the drone flight. So you can see here that with the helicopter, the birds all flush. And so the helicopter is very disturbing to the birds, versus the drone here, we flew at 15 meters above the birds. So it was not very high at all. And you can see their behavior at first glance, it really doesn't look like they've changed or done anything. And so we'll be going back and analyzing the videos to see if there is a change in behavior or not with the drone, and how the disturbance levels are different between helicopters and drones and manned aircraft surveys. So future work, so the spring and summer, we're going to continue to develop how we're going to conduct these waterfowl abundance surveys with the drones. And then next fall and winter, we're going to continue to collect waterfowl imagery and waterfowl behavior responses. And we'll continue to collect these waterfowl abundance survey data. And then we'll do all of the analyses kind of next spring and summer to wrap it up, to really see what the best way to survey for these birds are and how they respond to the drone. So with that, I'd like to thank the area managers that allow us to fly our drones on their conservation land, and Stephen F. Austin State University and their drone program for getting me involved in the drones. And with that, are there any questions?
We have time for questions since we're actually on a break now. So go ahead and ask Reid any questions you might have.
Hey, Reid. This is Trent Rohr at South Dakota State University. I was wondering if you have any goals to add sex into those questions or into your models, or if you're just going to strictly just stay with species.
Yeah, so we'd like to add sex. Kind of the problem with sex, or kind of what we've run into so far, is from the air and the images, a lot of the females look just kind of like brown birds, especially in early fall. So right now we're labeling by species and sex when we're able to tell. Otherwise, it's just kind of an unknown female bird. So we'd like to add that. We're not sure how feasible that's going to be yet.
Okay, awesome. Thanks.
Reid, this is Susan Feligi from the University of North Dakota. I have a question about the platform and the sensor that you're using and the flights. Maybe I missed this, but what exactly are you using for your aircraft and the camera? Are you doing stills or is it video?
Yeah, so we're using the DJI Mavic Pro 2, which is the drone he's actually holding in his hand there in that image. And we're using just the standard stock camera that comes on the drone, and we're currently doing still images. Yeah.
And then what altitude are you flying at?
So we're flying we've been flying at 120, 90, 60, 30, and 15 meters just to collect the images. All of the images, or most of the images you saw in the presentation, those were all at 15 meters. And so at 15 meters and 30 meters, we feel fairly confident in identifying, at least manually identifying species and sex. But then, above that, it gets very hard with the resolution we're getting. But we might be able to identify and still detect birds fairly well at 60 or 90 meters.
Are you having any issues with glare off the water and being able to discern species from that?
Yeah, so that's kind of going back to that, the environmental conditions and sunny versus cloudy days that we're kind of talking about. So we're still looking at the differences on the days and glare in the water from the water and kind of seeing how that affects everything. We're still kind of looking at all that.
Okay, thank you.
All right, so we are officially on a break right now. We will resume talks at 2:50. So yeah, if you have any questions for Reid, go ahead. Otherwise, take a chance to go stretch your legs and get a drink. Thanks. So Reid and Ben, looks like Brian Pauly submitted a comment / question for you. Specifically, Ben, in your study in particular, it seems a fixed wing model may be more quiet and less disturbing. Your thoughts? Mm.
Well, so I guess I can't speak for Ben, but this is Reid. And I guess one of the reasons we are using the rotary wing versus a fixed wing is ease of like takeoffs and landings. Since we're working on these wetlands, a lot of our takeoffs and landings are from the back sides of levees or tops of levees. And so it's a lot easier for us and say, or I guess kind of safer to be using these rotary drones instead of the fixed wings.
Great. Thanks, Reid. All right.